Now we come to chapter 3. In chapter 2, we have obtained the solution of Fredholm integral equation of second kind with degenerate kernel and established the theory of Fredholm alternative. In chapter 3, we shall consider kernel in more general form, that is continuous kernel and square integrable kernel. In this chapter, we shall slowly establish the theory of Fredholm alternative for more general form of kernel. This chapter is divided into 6 modules. In the first module, we shall use the method of successive approximations to solve Fredholm integral equation of second kind with continuous kernel. Now, we shall consider integral equation of second kind of Fredholm type as given by equation 3.1 for solution. We shall solve this integral equation by a method known as method of successive approximations. Here in the integral equation 3.1, the forcing function and the kernel kxt are continuous in the closed interval a b and in the square closed interval a b cross closed interval a b respectively. Now, this integral equation given integral equation 3.1 can be alternately written in the operator form as given by this, where I is the identity operator and capital K is the linear operator defined by the relation given by this. This is also discussed before. We shall now use the method of successive approximations to obtain the solution of the given integral equation 3.1. For this, we denote phi naught x as the 0th approximation of phi x, and in equation 3.2 we have used 2 types of symbol. One is phi naught x, another is phi superscript x. At 0th approximation, both are same and both are equal to the forcing function f x as given in equation 3.2. So, phi naught x is the 0th approximation. We now substitute phi naught t, that is the 0th approximation, in the integral of equation 3.1, which is on the right hand side. We substitute phi naught x in place of phi t to obtain the first approximation phi 1 x of phi x as given by phi 1 x equal to f x plus lambda integral a to b k x t phi naught t dt. We write this equation in the form as given by equation 3.3. Here f x, if you remember that it is equal to phi superscript naught x as given in equation 3.2, we use that in place of f x, and this phi superscript 1 x in equation 3.3 is given by this expression, or in the operator form phi superscript 1 x is given by this. It is related to phi superscript 0 x. So, from equation 3.3 you see that first approximation phi 1 x of the solution of given integral equation has been expressed as sum of phi superscript naught x plus lambda phi superscript 1 x. Now, we obtain the second approximation phi 2 x of phi x by substituting as before phi t, rather phi 1 t in place of phi t in the integral of the right hand side of equation 3.1, and we obtain phi 2 t, that is the second approximation, as given by this. I now substitute in place of phi 1 t, that is the first approximation, this expression as given by 3.3, so that phi 2 x, which is the second approximation to phi x, becomes equal to phi superscript naught x plus lambda integral a to b k x t phi superscript naught t plus lambda phi superscript naught t dt. We know that phi superscript 1 t dt is given by this expression. So, for this part we substitute lambda phi superscript 1 x, and for this part we have lambda square phi superscript naught x, where phi superscript naught x is given by this expression also in the operator, which is also given as the operator form. So, phi 2 superscript 2 naught phi superscript 2 x is equal to integral a to b k x t phi superscript 1 t dt. So, you can see from this expression that second approximation phi 2 x of the solution of given integral equation has been expressed as sum of three terms. They are phi superscript naught x plus lambda phi superscript 1 x plus lambda square phi superscript naught 2 x. So, we can continue in this way, and we define phi superscript j x as the integral a to b k x t phi superscript j minus 1 t dt, which is in the operator form can be written as capital K operating over phi superscript j minus 1 x, which gives back phi superscript j x as given in the equation 3.4. J runs from 1 to n. So, with this definition we can continue in similar manner to find successive approximations of phi x, and we say that phi capital N x of phi x
as the nth approximation to the solution of phi x of the integral equation, and we obtain phi capital N x as the sum given in equation 3.5. Now, we shall show that the above sequence phi n x converges to unique solution phi x of the integral equation 3.1 under certain special restriction on the values of lambda. Now, if we assume that f x and k x t are continuous functions, then we see that phi superscript not x is also continuous, and if phi superscript not x is continuous and k x t is continuous, then for j equal to 1, 2, etc., we find that phi superscript j x is also a continuous function. Now, we denote by small m as the supremum of mod f x, x belonging to closed interval a b, and by capital M we denote supremum of the kernel mod k x t, where x and t both belongs to closed interval a b. So, defining in this way, we find that mod of phi superscript not x equal to mod of f x. Mod of f x is less than its supremum value, that is capital M. Similarly, phi superscript 1 x, if we take the absolute value, then that will give you mod of integral a to b k x t phi superscript not t dt, which is less than equal to integral a to b mod k x t into mod phi superscript not t dt. Now, capital M is the supremum value of k x t and phi superscript not x is less than equal to M. These two combined together will give mod of phi superscript 1 x is less than equal to small m into capital M into b minus a. Similarly, mod of phi superscript 2 x, which is less than equal to integral a to b mod k x t mod phi superscript 1 t dt. Now, mod k x t less than equal to capital M and mod phi superscript 1 t dt is less than equal to small m into capital M b minus a. Combining these results, we see that absolute value of phi superscript 2 x is less than equal to small m into capital M square b minus a whole square. If we continue in similar way, we find that absolute value of phi superscript n x is less than equal to small m into capital M to the power n into b minus a whole to the power n, as given in equation 3.6. So, we have obtained the estimates of phi superscript j x from equation 3.6. If we use these estimates in equation 3.5, we can get an estimate of nth, capital Nth approximation phi capital Nx as given in equation 3.7. Now, if I make capital N tends to infinity in equation 3.7, the summation will converge absolutely and uniformly in the closed interval AB if rho equal to mod of lambda into capital M into B minus A, this is less than 1, as given by equation 3.8. Because we know that summation n equal to 0 to infinity rho to the power n equal to 1 by 1 minus rho if mod rho is less than 1. We have applied the same concept. So, from 3.8 we see that lambda mod of lambda should be less than 1 by capital M into B minus A. So, if this condition happens, then only the series in the right hand side of equation 3.7 will converge absolutely and uniformly. So, if lambda satisfies the condition 3.9, then the sequence phi capital Nx converges to the continuous limit function phi Lx, and we write phi Lx equal to summation n equal to 0 to infinity lambda to the power n into phi superscript Nx as given by equation 3.10. Now, in equation 3.10, from the summation we separate out the term corresponding to n equal to 0, so that we can write phi Lx equal to phi superscript naught x plus summation n equal to 1 to infinity lambda to the power n phi superscript n x. Now, we have seen that phi superscript naught x is equal to f x as given by relation 3.2. So, we just write f x in place of phi superscript naught x to get phi Lx equal to f x plus summation n equal to 1 to infinity lambda to the power n phi superscript n x. Now, we make some simplification at this point. We operate both sides of this equation by the operator lambda k, and then add f x on both sides to get this expression. Now, we can write this expression after some simplification. We know that this expression capital K phi superscript n x, this is equal to phi superscript n plus 1, and we can use that to get this expression. Now, the summation n equal to 1 to infinity lambda n plus 1 phi n superscript n plus 1 x, if it is expanded, it gives this form of right hand side. Now, from equation 3.10 10, you see that the summation is phi naught x, but rather phi superscript naught x plus lambda phi superscript 1 x plus summation n equal to 2 to infinity lambda n phi superscript n x. Using this, we can write this summation as phi L x minus phi naught x minus lambda into phi superscript 1 x. So that this summation gets simplified by this term. So, if we use this term in place of this summation, we get the expression as this. That is, this expression can be written in this form. Now, this phi superscript naught x from relation 3.2, we know that this is equal to f x. So, this term cancels with this term, and lambda k, capital K phi superscript naught x, this is equal to lambda into phi superscript 1 x, as is evident from equation 3.4. So, this term cancels with the last term lambda phi superscript 1 x. So, this whole expression becomes f x plus lambda k phi L x equal to phi L x. Or if I write this expression in the operator form, I find that phi L x satisfies equation 3.11. So, equation 3.11, you see that phi L x satisfies the given Fredholm integral equation of second kind as given by 3.1. That means, we have proved that phi L x is the solution of given Fredholm integral equation.
So far, we have obtained the solution of integral equation of Fredholm type of second kind in form of an infinite series. Now, we shall prove the uniqueness of the solution.
Now, we shall show that the solution phi L x of the given integral equation is unique. In order to show that the above solution phi L x is the only continuous solution of the integral equation 3.1 under the restriction of on lambda as given by equation 3.9, we proceed as follows. We assume that the solution is not unique and let psi x be another possible continuous solution of equation 3.1 other than the solution phi L x for values of lambda for which condition 3.9 is satisfied. We then find that phi L x minus psi L x, they satisfy the homogeneous form of the given integral equation, because phi L x satisfies the given integral equation as well as psi x also satisfies the given integral equation. So, their difference satisfies the corresponding homogeneous integral equation. So, this gives phi Lx minus psi Lx equal to lambda into capital K operating on phi L minus psi L x. Now, we expand this operator form and take the absolute value both sides to see that mod of phi Lx minus psi x is less than equal to mod lambda into integral a to b mod kxt into mod phi Lt minus psi Lt dt. Now, the supremum of the kernel kxt is capital M. So, we find that mod phi Lx minus psi x is less than equal to mod lambda into capital M into integral a to b mod of phi Lt minus psi t dt. At this point, we integrate both sides with respect to x from a to b. So, the left hand side becomes integral a to b mod phi Lx minus psi x dx, and this is less than equal to mod lambda into m b minus a into integral a to b mod phi Lt minus psi t dt as given in equation 3.12. If you recall equation 3.9, you will find that the expression mod lambda m into b minus a, this is strictly less than 1. So, if we use this, then we find that the left hand side of equation 3.12 is strictly less than integral a to b phi Lt minus psi t, its absolute value, into dt. So, this the fact that phi L and psi are continuous in the closed interval a b, we find that we must have phi Lx equal to psi x, and this shows that phi Lx is the only continuous solution of 3.1 provided condition 3.9 is satisfied. That means, we have proved the uniqueness of phi Lx. So, we have established that the function phi x, which we denoted by phi Lx, is given by the series 3.14. This is an infinite series where the functions phi superscript n x are defined by the relations 3.4. This represents the unique continuous solution of the Fredholm integral equation 3.1 under the condition 3.9 on the values of lambda. So, we have obtained in 3.14 the solution of the given integral equation in series form, and this series in equation 3.14 is called the Neumann series representation of the integral equation 3.1. Now, the function phi n x as given by relation 3.5 is the nth approximation to the solution phi x of the integral equation 3.1. If we denote by epsilon n x as the error at nth stage, then epsilon n x is defined as phi x minus phi n x, that is equal to summation n equal to n plus 1 to infinity lambda n phi superscript n x. So that mod value of epsilon n x gives summation small n equal to capital N plus 1 to infinity mod of lambda to the power n into mod of phi superscript n x. Now, if we note the relation 3.6, we find that epsilon n x is less than equal to small m into summation small n equal to capital N plus 1 to infinity mod lambda into capital M into b minus a whole to the power small n, and which tends to 0, this is less than 1. So, it tends to 0 as capital N tends to infinity for lambda satisfying the condition 3.9. This shows that the error epsilon n x at nth approximation tends to 0 as capital N tends to infinity. So, we have used successfully the method of successive approximation to find out the solution of the integral equation 3.1. Thus, in module 1 of chapter 3, we have obtained the solution in an infinite series form of Fredholm integral equation of second kind with continuous kernel and continuous forcing function by using the method of successive approximation.